Tonight, we're going to start with something that most people never stop to think about. And once you do, it changes the way you look at the sky. You probably picture Earth as a planet in space, a rocky ball orbiting the sun from a comfortable distance of 93 million miles, safely separated from it by the void. That picture is wrong, not slightly wrong. Fundamentally wrong. Earth doesn't orbit the sun from outside its influence. Earth orbits from inside it. The sun's outer atmosphere, a region of superheated plasma called the corona, doesn't end at the visible surface. It extends outward through the solar system in the form of the solar wind, a constant stream of charged particles racing outward at roughly 1 million miles per hour. That stream reaches well past Earth. It reaches past Mars, past Jupiter, past Saturn, past Uranus and Neptune, all the way out to a boundary called the heliopause, roughly 120 astronomical units from the Sun. Earth, at 1 astronomical unit, sits deep inside it. Every human being who has ever lived has spent their entire existence within the outer atmosphere of a star. Think about that for a second. We don't orbit the sun from a safe distance. We orbit from inside it. The solar wind is passing through you right now. It passed through every person who ever walked on this planet. It's not a metaphor, it's physics. This changes the question you should be asking. Most people look at space and worry about the void, the cold, empty darkness between stars, the nothingness. And it's true that interstellar space is about as hostile an environment as you can imagine. But here's the thing. The void is mostly just empty. What surrounds us right now is not empty at all. It's a turbulent, electromagnetically charged environment driven by a star that is, even at this distance, constantly reaching out and touching everything in the solar system. The threats worth understanding don't come from out there, far away in the dark. They come from 2 directions much closer to home, above the sun. And by above, we mean outward through the corona, through the region where the sun's magnetic field twists into violent configurations and hurls billion-ton clouds of plasma into space. And below, in a different sense, outward through the solar system itself, past the familiar planets, into the regions where hundreds of thousands of icy objects orbit in the dark, held loosely in place by a gravitational balance that passing stars and the tidal forces of the Milky Way have been quietly disrupting for billions of years. Those are the 2 directions we're going to travel tonight. Above the sun, the corona burns at 2 million degrees Fahrenheit, which is roughly 200 times hotter than the surface directly below it. That alone should stop you cold. The surface of the sun is around 10,000 degrees. The atmosphere above it is 2 million. That's not how heat is supposed to work. It violates every intuition you have about how energy behaves, and we still don't fully understand why it happens. Out of that corona come solar flares, eruptions of electromagnetic radiation that travel at the speed of light and reach Earth in 8 minutes, with essentially no warning. Out of it come coronal mass ejections, physical walls of magnetized plasma that have, on at least 1 documented occasion in recent history, come within 9 days of hitting Earth hard enough to collapse power grids across entire continents. Beyond the planets, the outer solar system holds reservoirs of objects we've barely catalogued. The Kuiper Belt, the Oort cloud, a theoretical shell of perhaps 1 trillion icy bodies stretching nearly halfway to the nearest star, so delicately balanced that a passing star can shake loose millions of them at once and send them falling inward toward the sun, toward us. And between the stars themselves, rogue planets drift in total darkness, untethered to any star, cold and essentially invisible. None of this is speculation. It's documented, studied, and in some cases narrowly survived. And by the time we're done, you'll understand why the void between the stars isn't the thing that keeps solar physicists up at night. Let's start above the sun, because that's where things stop making sense almost immediately. The sun has a visible surface called the photosphere. That's the bright disk you see when you look at the sun through a solar filter, the glowing yellow-white layer that defines where the star ends and space begins. The photosphere burns at roughly 10,000 degrees Fahrenheit. That is extraordinarily hot by any human standard. Hot enough to vaporize every material we've ever engineered. And yet, compared to what sits directly above it, 10,000 degrees is almost mild. The corona is the sun's outer atmosphere. It begins just above the photosphere and stretches outward for millions of miles, gradually thinning into the solar wind that fills the inner solar system. During a total solar eclipse, when the moon blocks the photosphere, the corona becomes visible, a ghostly white halo of tendrils and loops extending far beyond the sun's edge. It looks peaceful from here. It is not peaceful. Here's the problem. The corona reaches temperatures of roughly 2 million degrees Fahrenheit, not warmer than the surface, not twice as warm, 200 times hotter than the surface sitting directly beneath it. If you walked away from a campfire, the air temperature would drop. Walk far enough and you'd be cold. That is how heat behaves in every context humans have ever experienced. Energy dissipates as it moves away from its source. But above the sun, the opposite happens. The temperature climbs as you move outward, dramatically, incomprehensibly. This is not a minor anomaly. This is a direct violation of basic thermodynamic intuition, and it has been one of the central unsolved problems in astrophysics for more than 80 years. We've known about the coronal heating problem since the 1940s, when Swedish physicist Bengt Edlund identified spectral lines in the corona that could only be produced at temperatures of millions of degrees. Astronomers at the time assumed there was a measurement error. There wasn't. So where is all that heat coming from? The short answer is, we're still working on it. The longer answer involves magnetic fields, and the sun has those in extraordinary abundance. The leading explanation is that the sun's magnetic field is the culprit. The photosphere is covered in convection cells, churning columns of plasma that rise, cool, and sink back down continuously. This constant churning drags magnetic field lines around, twisting and braiding them into increasingly complex configurations. When those field lines become too tangled, they release their stored energy. That energy has to go somewhere. The leading theory is that it goes into heating the plasma above, into the corona. But exactly how that energy transfers is where scientists disagree. There are two main competing ideas. The first is called wave heating. As the magnetic field lines are jostled by the convection below, they vibrate. Those vibrations travel upward along the field lines as magnetohydrodynamic waves, Alfvén waves specifically, carrying energy into the corona. When those waves break or dissipate, they deposit that energy as heat. The corona absorbs it the way a microwave absorbs electromagnetic radiation. The plasma heats up. This mechanism is real. We've detected Alfvén waves moving through the corona. The question is whether they carry enough energy to account for the full 2 million degree temperature, and the math has been difficult to close. The second idea is called nanoflare heating, proposed by physicist Eugene Parker in the 1980s. Parker suggested that instead of a continuous wave process, the heating happens in countless tiny explosions, nanoflares, each one releasing a small burst of energy as stressed magnetic field lines snap and reconnect. No single nanoflare is large enough to detect directly, but Parker argued that trillions of them firing constantly across the solar surface could collectively heat the corona to observed temperatures. It's like saying you can't hear any individual raindrop hitting a tin roof, but together they make a roar. The problem is that nanoflares are, by definition, below our detection threshold. Proving they exist in sufficient numbers to drive coronal heating has been extremely difficult. Most researchers today suspect the answer involves both mechanisms, operating in different regions and at different scales. But that's an educated guess more than a confirmed theory. Then there's what the Parker Solar Probe found. Launched in 2018, the Parker Solar Probe is the closest to the Sun any spacecraft has ever traveled. Its mission is to fly directly through the corona, a feat that required engineering a heat shield capable of enduring temperatures that would vaporize steel. As it flew through the inner corona, it detected something unexpected. Packets of superheated plasma traveling outward from the Sun. These weren't large solar events. They were discrete structures, pockets of material far hotter than the surrounding corona, moving through it like bubbles rising through water. Scientists described them informally as heat bombs. The idea is that these structures form below the corona, in the churning turbulence of the photosphere, and then travel upward. When they reach the corona, they release their stored energy explosively, dumping heat directly into the surrounding plasma. The Parker Solar Probe didn't find these because we expected them. It found them because it was close enough to detect what earlier spacecraft had missed entirely. And now the working picture of coronal heating has to account for heat bombs as one additional mechanism layered on top of wave heating and nanoflares. That's 3 possible mechanisms, and the field still isn't settled on which one dominates, or under what conditions, or how they interact. Think about that for a second. We have been studying the Sun continuously, with increasingly sophisticated instruments, for the better part of a century. We have sent spacecraft to skim through its atmosphere. We have detected its vibrations, mapped its magnetic field, cataloged its eruptions, and we still can't fully explain why its outer atmosphere is 200 times hotter than its surface. That gap in understanding matters more than it might seem. The corona isn't just a physics puzzle. It's the source of everything that emerges from the Sun and moves outward through the solar system. Solar flares originate in the corona. Coronal mass ejections, the billion-ton plasma clouds we'll talk about shortly, form in the corona. The solar wind that extends past Earth and fills the inner solar system is essentially the corona expanding outward continuously. If we don't understand what's driving the corona's behavior, we can't fully predict what it will produce. And the corona is not a stable, uniform structure. It changes constantly. Magnetic loops rise from the surface and collapse back. Streamers form and break off. Holes open in the corona where the magnetic field points outward rather than looping back, allowing solar wind to pour directly into space at higher speeds than normal. The corona during solar maximum, when the sun's activity cycle reaches its peak, looks completely different from the corona during solar minimum. It is in a constant state of dynamic, violent flux. The temperatures involved are almost beyond analogy. 2 million degrees Fahrenheit is hotter than the outer shells of many stars. It is so hot that the plasma in the corona emits strongly in X-rays, not visible light, X-rays, which is why the corona is essentially invisible to the naked eye under normal circumstances. Its light is in the wrong part of the spectrum. We have to use specialized instruments to see it directly, and yet it is physically surrounding us. That 2 million degree envelope extends past Earth's orbit. The planet you're standing on right now is inside the corona's extended influence, bathed in the particles it constantly sheds. We don't fully understand why it's that hot. We have good ideas. We have multiple spacecraft gathering data. We have models that reproduce some of what we observe. But the full, settled, confirmed answer to why the corona exists at 2 million degrees while the surface below it sits at 10,000, that answer is still being worked out. The corona isn't decorative. It's the engine that generates everything heading toward us, and we still don't fully understand how it runs. A solar flare is, in the simplest terms, a sudden explosion of electromagnetic radiation from the sun's surface, and the reason it's terrifying is the part that comes after sudden. The radiation travels at the speed of light. That's 186,000 miles per second. The sun is about 93 million miles away. Do the math and you get roughly 8 minutes, which sounds like enough time to do something, until you realize that the flare itself is what you're detecting. By the time any instrument on Earth registers the event, the radiation is already here. There is no warning window. There is no gap between the alarm and the impact. The alarm is the impact. Let's back up and talk about what a solar flare actually is. When magnetic field lines in the sun's corona become so twisted and stressed that they can no longer hold their configuration, they snap and reconnect violently. That reconnection releases an enormous amount of stored energy in a very short time, sometimes in minutes. The energy comes out as radiation across the entire electromagnetic spectrum. Radio waves, visible light, ultraviolet, X-rays, gamma rays, all of it simultaneously, all heading outward at the speed of light in every direction the flare faces. If Earth is on that side of the sun, every bit of it is coming straight at us. The X-ray and ultraviolet components are what cause the most immediate damage. When they slam into the upper atmosphere, they ionize the gas in the ionosphere, the layer that radio waves bounce off of to travel around the planet. That ionization disrupts the reflection. High-frequency radio, the kind used by aircraft on long-distance routes, simply stops working. It doesn't degrade, it doesn't get staticky, it goes silent. Pilots flying polar routes over the Arctic and Antarctic lose contact with air traffic control almost instantly. GPS satellites use radio signals too, and those signals have to pass through the ionosphere to reach receivers on the ground. A strong flare bends and delays those signals in unpredictable ways, introducing errors that can push a calculated position off by meters or more. For a passenger aircraft, that's manageable. For a military drone, a precision landing system, or a ship navigating a narrow harbor entrance, it's a serious problem. Here's where things get uncomfortable. These disruptions happen even during moderate flares. The sun produces dozens of smaller flares every month during active periods, and each one causes some level of ionospheric disturbance. The ones that make people nervous are classified as X-class, the strongest category in the flare rating system. An X1 flare is already powerful enough to cause radio blackouts on the sunlit side of Earth. An X10 is 10 times more energetic. The strongest flare ever recorded, observed in 2003 during what became known as the Halloween solar storms, overwhelmed the measuring instruments designed to classify it. The sensors maxed out at X17 before going offline. Later analysis suggested the actual peak was somewhere around X28 to X45. We don't know exactly. The instruments couldn't keep up. During those Halloween storms, the people watching the data at NOAA's Space Weather Prediction Center were not having a quiet night. Power grid operators were receiving alerts and scrambling to adjust load flows to prevent transformer damage. Satellite operators were putting their spacecraft into safe modes, reducing the surface area exposed to charged particles, hoping the hardware would survive. Airlines were rerouting flights away from polar regions, adding hours to transoceanic journeys. The Swedish power grid experienced a blackout. Transformers in South Africa were damaged. FAA systems experienced GPS positioning errors that disrupted air traffic management across parts of the United States. And that was a flare event, not a coronal mass ejection, not a combined event, just radiation, arriving at the speed of light, doing what radiation does. What makes this particularly unsettling is that the 2003 Halloween storms were not the strongest flares in recorded history. They were simply the strongest we had instruments sophisticated enough to measure in real time. The effects were severe enough to cause billions of dollars in disrupted commerce. Yet the infrastructure systems affected were designed assuming a certain baseline of solar behavior. Satellite designers had to go back and rethink their protection strategies. Operators of critical infrastructure had to revise their emergency protocols. But the underlying vulnerability remained: our dependence on systems that can be disrupted by events we cannot predict with precision or prevent with any technology currently available. The flares continue. The sun continues its cycle. The gaps in our ability to forecast and respond remain largely unchanged. The cascading failure problem is what keeps grid engineers up at night. Modern infrastructure is not a collection of independent systems. It's a web of interdependencies, where each node assumes the others are functioning. The power grid depends on communications networks to coordinate switching and load balancing. Communications networks depend on the power grid to run their equipment. GPS timing signals are embedded in financial transaction systems, mobile networks, and data centers in ways most people never think about. The timestamps that synchronize distributed systems, the precise timing that makes 4G and 5G networks function efficiently. When GPS degrades, those systems don't fail immediately, they drift. Errors accumulate, and the people managing those systems may not immediately understand why. A sufficiently powerful X-class flare, particularly one with a long duration, can push ionospheric disruption to levels where GPS becomes unreliable across entire hemispheres for hours. During that window, aviation approaches using GPS-based systems go to backup procedures. Some ports stop operating. Financial systems flag anomalies. None of this is catastrophic on its own, but it all happens at once, and the people responsible for each piece of infrastructure are simultaneously dealing with their own piece of the problem, while depending on systems that are equally degraded. Scale that up. The largest flares in the historical record weren't just stronger versions of what we normally see. They were categorically different in energy. The 774 CE event detected in tree rings through anomalous carbon-14 spikes appears to have been a solar particle event roughly 10 times more powerful than anything recorded in the modern era. We have no direct observations of it. We have isotopes in ancient wood. If something comparable happened today, the ionospheric effects would dwarf anything we've experienced in the satellite age. Transformers would be at risk not just from geomagnetic storms, but from the direct radiation effects. High-altitude aircraft could receive elevated radiation doses. Astronauts on the International Space Station would be sheltering in the most shielded sections of the vehicle and hoping the storm passed quickly. The forecasting situation is genuinely difficult. Solar physicists can identify active regions on the sun, areas of intense magnetic field activity, clusters of sunspots, and flag them as potentially flare productive. That's roughly where the predictive capability ends. We can say a region is capable of producing a significant flare. We cannot reliably predict when. We cannot predict the exact magnitude. The difference between an X1 and an X10 is not something we can see coming. Even the most sophisticated models of solar magnetic field evolution struggle to get the timing right within a window smaller than several days. For practical warning purposes, forecasters working in real time are often watching the data from instruments that detect the flare as it happens and issuing alerts within minutes, which is better than nothing, but not meaningfully better than nothing when the thing you're alerting people to is already hitting their infrastructure. There's another layer to this. The sunlit side of Earth is the side that takes the direct hit from a flare's radiation. At the moment the flare peaks, everything on the day side experiences the ionospheric disruption simultaneously. But Earth rotates. An active region on the sun doesn't produce just one flare. It often produces a series, sometimes over days or weeks, as the magnetic field continues to churn and reconnect. The Halloween storms of 2003 produced multiple major flares over the course of about 2 weeks. Each one hit a different set of longitudes depending on where Earth was in its rotation. There's no safe side of the planet to be on across an extended active period. Before we get too comfortable with the idea that we at least understand the threat, it's worth sitting with what we don't know. The active regions that produce the most violent flares often look completely normal the day before, which is not a reassuring thing to know. If a solar flare is a gun, a coronal mass ejection is the cannonball. And the one that almost hit us in the summer of 2012 would have changed everything. We spent the last section talking about radiation. Electromagnetic energy traveling at the speed of light, hitting Earth 8 minutes after it leaves the sun. That's terrifying enough. But a coronal mass ejection is a different category of event entirely. It's not energy. It's matter. Billions of tons of magnetized plasma, physically ripped from the sun's outer atmosphere and hurled into space at speeds ranging from about 200 kilometers per second on the slow end to more than 3,000 kilometers per second for the most violent events. To put that in perspective, the faster CMEs are traveling at roughly 6.7 million miles per hour. That's not a figure of speech. That's just the number. The distinction matters because flares and CMEs often happen together, and it's easy to blur them into a single threat. A flare arrives first. The radiation hits in minutes. The CME follows, taking anywhere from 15 hours to a few days to cover the 93 million miles between the Sun and Earth. When both happen in sequence, which is common during major solar events, the flare's radiation can actually preconditioning space ahead of the CME, making the geomagnetic effects worse when the plasma cloud finally arrives. They work together, not cooperatively. The Sun doesn't plan anything, but the timing often lines up in ways that amplify the damage. Here's what happens when a CME reaches Earth. Our planet has a magnetic field generated deep in the molten iron core, and that field forms the magnetosphere, an invisible bubble that deflects most of the solar wind flowing past us at all times. Under normal conditions, the magnetosphere holds. When a CME arrives, it carries its own embedded magnetic field, and if that field is oriented in the right direction, specifically pointing southward, opposite to Earth's northward field, the two fields can reconnect technically. The process is called magnetic reconnection, and when it happens, the CME's plasma pours into Earth's magnetosphere like water through a broken dam. The magnetosphere compresses on the day side, the side facing the Sun. On the night side, it stretches out into a long tail. The whole structure gets distorted, energized, unstable. Currents are driven through Earth's upper atmosphere. Particles are accelerated. The Van Allen belts, those rings of trapped radiation orbiting Earth, get flooded with additional high-energy particles. Satellites operating in those regions start accumulating electrical charge on their surfaces. GPS signals become unreliable. And on the ground, something worse happens. The intensity of a CME impact depends on several variables that can shift the difference between a manageable event and a catastrophic one. The speed of the ejection matters. Faster CMEs compress the magnetosphere more violently. The magnetic field strength embedded in the plasma matters. The size of the CME matters. And crucially, the orientation of that embedded magnetic field matters more than almost anything else. A CME that might pass with minimal impact if its field points northward can devastate Earth's systems if that same field points southward. Scientists call this angle the all-important BZ component, and it's the primary factor determining whether a CME will trigger a severe geomagnetic storm or a mild one. The unpredictability of this orientation means we cannot simply calculate risk from velocity alone. A slower CME with perfect field alignment can be more dangerous than a faster one with unfavorable orientation. Geomagnetically induced currents. This is the mechanism that turns a space weather event into an infrastructure crisis. When the magnetic field around Earth fluctuates rapidly, it induces electrical currents in any long conductor sitting on or near the surface. Power lines qualify, pipeline networks qualify. The longer the conductor, the stronger the induced current. And modern power grids are, functionally, enormous conductors spanning entire continents. The measure scientists use to track how bad a geomagnetic storm is getting is called the DST index, Disturbance Storm Time. It measures the change in Earth's horizontal magnetic field at the equator. During a quiet period, DST sits near zero. During a minor storm, it might drop to -30 or 50 nanots loss. During a severe storm, the kind that causes widespread grid problems, it drops below -200. The Carrington event of 1859 is estimated to have pushed the DS index to somewhere around -850, maybe worse. We're not sure because we weren't measuring it directly. We're reconstructing the number from sediment cores and historical records. What we do know is what actually happened on the ground. September 1st and 2, 1859. British astronomers Richard Carrington and Richard Hodgson independently observed a massive solar flare, the first ever directly observed by humans. About 17 hours later, the associated CME arrived. That's fast, exceptionally fast. The plasma was moving at roughly 2,300 kilometers per second. The geomagnetic storm that followed was unlike anything before or since in recorded history. Auroras appeared as far south as Cuba, Colombia, and Hawaii. People in the northeastern United States could read newspapers by the light of the aurora in the middle of the night. Gold miners in the Rocky Mountains woke up, saw the glow, and started making breakfast, convinced it was morning. The telegraph network was the most advanced long-distance communication technology of the era. It was also, functionally, a continental grid of conductors, exactly the kind of infrastructure that geomagnetically induced currents devastate. Operators reported sparks flying from their equipment. Some received electrical shocks. Fires broke out at telegraph stations. And here's the detail that illustrates just how strong the induced currents were. Some telegraph operators, after disconnecting their batteries entirely, found that their systems were still transmitting. The Earth itself was providing enough current to run the network. They were communicating on power from the geomagnetic storm. The financial systems of 1859 had no dependence on electrical systems. Banking was conducted through written correspondence and physical transfers of currency and securities. Transportation relied on horses and trains powered by mechanical means rather than electrical grids. Food supply chains, while fragile by modern standards, did not depend on refrigeration or electronic tracking. Even the fastest communication was limited by telegraph speeds that, while revolutionary for their time, were measured in words per minute rather than the instant global information transfer we now take for granted. A Carrington event in 1859 caused disruption, certainly, but disruption that a pre-industrial society's infrastructure could ultimately absorb and overcome. The consequences were uncomfortable and economically damaging, but not civilization-threatening. That fundamental fact cannot be overstated when considering modern vulnerability. Now think about what we've built in the 166 years since then. Carrington-level events are estimated to occur roughly once per century, possibly less frequently. The last comparable event was in 1921. Before that, 1859. We are statistically in the window. Some researchers put the annual probability of a Carrington equivalent CME at somewhere between 0.5 and 1.2%. That sounds small. Over a decade, it becomes meaningful. Over 50 years, it becomes likely. A 2013 study commissioned by Lloyd's of London estimated that a Carrington equivalent event hitting Earth today would cause between $0.6 and $2.6 trillion in economic damage in the United States alone. Recovery time for the most affected regions, particularly those where high-voltage transformers are destroyed, was estimated at 4 to 10 years, not months, years. High-voltage transformers are not off-the-shelf items. They weigh hundreds of tons. They're custom-built. Lead times for a single replacement unit can run to 18 months under normal manufacturing conditions. There are not enough spare transformers to replace the ones that would fail in a major event. There's no stockpile. There's no rapid response warehouse somewhere waiting for this scenario. Which brings us to July 2012. On July 23rd of that year, the Sun released one of the most powerful CMEs in recorded history. It was enormous, fast, dense, carrying an unusually strong magnetic field oriented almost perfectly to cause maximum damage if it struck Earth. Researchers who studied the event afterward concluded it was likely comparable to the Carrington event, and some analyses suggest it may have been stronger. Instruments aboard the Stereo A satellite caught the full blast of it. Earth did not. 9 days earlier, Earth had been in the path of that region of the Sun. 9 days later, it would have been again. The orbital geometry that placed us out of the firing line on July 23rd was not the result of preparation, of early warning systems, of planetary defense programs. It was chance. The Sun fired, and we happened to be somewhere else. Studies published in the years since have been consistent on the likely outcome if the timing had been different. Power grids across North America, Europe, and parts of Asia would have experienced geomagnetically induced currents strong enough to destroy high-voltage transformers on a wide scale. Satellite operations would have been severely disrupted. GPS would have been unreliable or non-functional for days to weeks. Radio communications across large portions of the planet would have gone down. Let's be specific about what the recovery period would actually look like, because abstract numbers don't fully communicate what this means. Without functioning power grids, fuel pumps don't run. Gas stations can't dispense fuel. Trucks can't deliver food to grocery stores. Water treatment plants require electricity to operate. Without it, municipal water systems that serve hundreds of millions of people fail within days. Hospitals on backup generators can survive for a limited period, but backup generators require fuel, and fuel requires functional supply chains, which require electricity. Medications that require refrigeration, insulin being the obvious example, begin degrading within days at room temperature. Communications networks, even those not directly damaged by the CME, depend on infrastructure that needs power. This is the cascading failure problem that makes a major geomagnetic storm categorically different from other disasters. A hurricane destroys a region. A Carrington-level CME degrades the systems that every region depends on simultaneously, at the same time, across entire hemispheres. There's no unaffected neighbor to send aid. There's no functioning logistics network to coordinate response. The scale is total in a way that most disaster planning frameworks aren't designed to handle. 9 days was the margin between the world we live in now and a world where most of the infrastructure holding civilization together simply stopped working. Here's something worth sitting with for a moment. Earth does not orbit the Sun from a safe, sheltered distance. That's the version of reality most of us carry around. The Sun is over there, 93 million miles away. We're over here. There's a lot of empty space between us, and that space acts like a buffer. It doesn't. The solar wind, the constant stream of charged particles pouring off the sun in every direction, doesn't stop somewhere between the sun and Earth. It flows past Earth. It flows past Mars. It flows past Jupiter and Saturn and Neptune, and it keeps going until it finally runs out of momentum somewhere between 80 and 100 astronomical units from the sun, in a region called the heliopause. The solar wind is technically an extension of the corona, which means Earth doesn't orbit outside the sun's atmosphere. It orbits inside it. Every person who has ever lived has spent their entire life inside the outer atmosphere of a star. Think about that for a second. So what exactly is flowing around us at all times? The solar wind is mostly protons and electrons, with a smaller fraction of alpha particles, helium nuclei stripped of their electrons. These aren't exotic hypothetical particles. They're real, fast, and constant. At Earth's distance, the solar wind arrives at roughly 1,000,000 miles per hour. Not during a storm. Not during a flare event. That's the baseline. That's Tuesday. The particle density is low, only a handful of particles per cubic centimeter. But the speed and the electromagnetic energy they carry are not trivial. This is the ocean we live in. It surrounds the planet continuously, and the only reason it doesn't strip away our atmosphere or irradiate everything on the surface is one thing: Earth's magnetic field. Earth's magnetic field creates what's called the magnetosphere, a vast region of space where Earth's magnetic influence dominates over the solar wind. On the side facing the sun, the magnetosphere is compressed by solar wind pressure to roughly 60,000 kilometers out from Earth's surface. On the night side, it stretches into a long tail extending hundreds of thousands of kilometers in the opposite direction. Within this structure sit the Van Allen belts, two donut-shaped regions of space filled with high-energy charged particles trapped by Earth's magnetic field. The inner belt sits roughly 1,000 to 12,000 kilometers above the surface. The outer belt extends from about 15,000 to 25,000 kilometers out. These belts are dangerous. Satellites passing through them accumulate radiation damage over time. Astronauts on the International Space Station are mostly below the inner belt, which is part of why low Earth orbit is considered relatively safe compared to what's waiting above. The magnetosphere doesn't just deflect the solar wind, it redirects it, channels it, and in doing so creates a protective cavity around Earth where life can exist. Without it, the solar wind would erode our atmosphere the way it has on Mars, which lost its global magnetic field billions of years ago and has been slowly losing its atmosphere ever since. Mars today has an atmospheric pressure less than 1% of Earth's. Part of that story is the solar wind, relentlessly chipping away with no magnetic shield to stop it. We are not Mars because we still have our magnetic field. That's the margin. The strength of this protection is remarkable but not unlimited. Earth's magnetic field generates roughly 50 microteslas of strength at the surface, measurable but not overwhelming in absolute terms. What matters is the geometry. The field extends outward in a dipole pattern, strongest at the poles and weakest near the equator, creating an asymmetrical shield that bends and channels the solar wind rather than stopping it entirely. This channeling is crucial. It means most of the energy from the incoming solar wind is redirected around the magnetosphere rather than being absorbed. The Van Allen belts, while dangerous to satellites and astronauts, represent the system working as designed, trapping and storing particles that would otherwise reach the surface. This is why astronauts in low Earth orbit experience far less radiation exposure than they would in the belts, and orders of magnitude less than they would without the magnetosphere entirely. Here's where things get uncomfortable. The magnetosphere holds under normal conditions, but the solar wind isn't always normal. During geomagnetic storms, driven by the CMEs and solar wind pressure spikes we just discussed, the magnetosphere gets compressed hard on the day side and destabilized. The Van Allen belts get injected with additional high-energy particles. The boundary layers of the magnetosphere become turbulent and partially permeable. Satellites in medium and high Earth orbits experience increased particle charging, which can damage electronics, corrupt sensor readings, and in severe cases permanently disable spacecraft. Satellites in low Earth orbit experience increased atmospheric drag because geomagnetic heating causes the upper atmosphere to expand, raising the density at orbital altitudes. This is what brought Starlink's freshly launched satellites down in 2022. A geomagnetic storm shortly after launch increased drag enough that 40 of 49 satellites couldn't maintain altitude and re-entered. A moderate storm, not even a severe one. During major geomagnetic storms, auroras appear far outside their normal polar regions. They've been seen over Florida, over Texas, over the Mediterranean. They're beautiful. They're also a sign that the magnetosphere is under serious stress. The same process producing the aurora, charged particles funneling down magnetic field lines and exciting atmospheric gases, is also injecting energetic particles into regions of the magnetosphere where they don't normally exist, and pushing radiation down toward altitudes where satellites operate. Now consider what all of this means for anyone who isn't sheltered by Earth's magnetic field. Astronauts on the moon have no magnetosphere above them. Astronauts traveling to Mars spend months in interplanetary space, where the only shielding against solar energetic particles is the walls of the spacecraft. Those walls are not thick. They can't be, because mass is expensive to launch. A major solar energetic particle event, the kind that accompanies large CME eruptions, can deliver radiation doses that exceed safe lifetime limits for astronauts within hours. NASA's guidelines for astronaut radiation exposure are based on career lifetime limits, and a single bad event during a deep space transit could consume a significant fraction of that budget in an afternoon. Mission planners know this. There's no clean solution. You can add more shielding, but shielding adds mass, and mass constrains everything else about the mission. You can try to schedule missions during solar minimum when activity is lower, but solar minimum doesn't mean zero activity. Some of the most powerful solar energetic particle events on record occurred during relatively quiet periods of the solar cycle. The sun doesn't check the calendar. The honest answer, when you push mission planners on this specific question, is that a crewed Mars mission would accept some level of radiation risk that we wouldn't accept for any other operational environment, and that an unexpected severe event during transit is a scenario they can mitigate but cannot fully solve with current technology. There's one more layer here that ties directly back to everything else. The solar wind doesn't just threaten us, it also protects us. The heliosphere, the enormous bubble of solar wind and magnetic field that the sun blows around the entire solar system, acts as a partial shield against galactic cosmic rays. These are high-energy particles accelerated by supernovae and other violent events in the galaxy, and they stream through interstellar space at close to the speed of light. The heliosphere deflects and absorbs a significant fraction of them before they reach Earth. During solar minimum, when the solar wind is weaker and the heliosphere is less robust, galactic cosmic ray flux at Earth increases. During solar maximum, the stronger solar wind pushes the heliosphere outward and reduces that flux. The very activity that produces dangerous flares and CMEs is also, at a system level, expanding the bubble that shields us from the galaxy. So the solar wind is doing two things simultaneously. It's the constant environmental threat, the ocean of charged particles that assaults our satellites, compresses our magnetosphere during storms, and would irradiate our astronauts without warning. And it's the thing keeping the galaxy out. Both are true at the same time. It protects us from the galaxy, it threatens us from the sun, and the line between those two things is razor thin and constantly moving. Now let's go the other direction, not above the sun, but through it, inward, toward conditions that make the surface look calm by comparison. The surface of the sun, the photosphere, sits at around 10,000 degrees Fahrenheit. That already sounds extreme, but the photosphere is essentially the sun's skin, and what's underneath it makes the surface look mild. As you descend inward, temperature and pressure climb in ways that quickly leave human intuition behind. By the time you reach the core, temperatures hit roughly 15 million Kelvin, not 15 million degrees Fahrenheit. Kelvin. At those temperatures, the difference between the two scales barely matters. Both numbers are so far outside anything we can meaningfully experience that analogies start to break down before you finish constructing them. The pressure at the core is approximately 250 billion times Earth's atmospheric pressure. Here's one way to think about that. The pressure at the bottom of the Mariana Trench, the deepest point in the ocean, about 7 miles down, is around 1,000 times surface pressure. That's enough to crush unprotected equipment instantly. Now multiply that by 250 million. That's the core of the sun. Every cubic meter of space at the center of this star is being compressed by the weight of an entire stellar mass sitting on top of it. Under those conditions, matter behaves in ways that have no analog on Earth. Atoms are stripped completely of their electrons. What exists in the core isn't gas in any conventional sense. It's plasma, a soup of bare nuclei and free electrons moving at extraordinary speeds, colliding constantly and occasionally fusing. That fusion is the entire point. Hydrogen nuclei slam together with enough force to overcome their mutual electromagnetic repulsion, combine into helium, release energy in the process. This is the reaction that has been powering the sun for about 4.6 billion years and will continue for roughly another 5 billion. Each fusion reaction releases gamma-ray photons, high-energy light, and here's where things get genuinely strange. Those photons don't travel from the core to the surface and then out into space. That's not how it works. The interior of the sun is so dense that a photon can't travel more than a fraction of a millimeter before it collides with another particle and gets absorbed. Then it's re-emitted, then absorbed again, then re-emitted in a completely different direction. This random walk through the solar interior, a process called radiative diffusion, is so slow, so tortured, that a single photon can take somewhere between 10,000 and 20 million years to complete the journey from the core to the surface. The estimates vary depending on the model, but even the conservative figures are staggering. Think about what that means for the light hitting your face right now. The energy in that sunlight was generated in the core of the sun millions of years ago, during a period when the ancestors of modern humans hadn't yet appeared. The photons bounced and scattered and re-emitted their way through the solar interior across geological time, finally reaching the surface. Then traveled the 93 million miles to Earth in just 8 minutes. 8 minutes for the last leg of a journey that took potentially 20 million years. The region where this slow diffusion happens is called the radiative zone. It extends from the edge of the core outward to about 70% of the sun's radius. It's not doing anything obvious from the outside. It's a vast, dense, extraordinarily hot region of plasma where energy is being transported upward one random collision at a time. Temperatures drop across this zone from roughly 15 million Kelvin near the core down to about 2 million Kelvin at the outer edge. By solar standards, that's cooling down considerably. Beyond the radiative zone, something changes. The plasma becomes less dense, and radiative diffusion stops being efficient. Instead, the sun switches to a different method of moving energy outward: convection. Hot plasma rises, cools at the surface, and sinks back down. Same basic principle as boiling water on a stove, except nothing about this is small. The convective zone extends from 70% of the solar radius all the way to the visible surface. It's roughly 125,000 miles thick. The convection cells rising and falling within it, called granules and supergranules depending on their scale, can be hundreds of miles across. Some of the larger structures span distances comparable to individual states or small countries. They rise, shed their heat at the photosphere, sink back down in loops that cycle on timescales of minutes to days. The surface of the sun, when you look at it through the right filters, is covered in these churning structures, constantly moving, constantly turning over. This convective churning matters for reasons that go far beyond simple heat transport. The plasma in the convective zone carries electrical charges. Moving charged plasma generates magnetic fields. And the sun doesn't rotate as a solid body. The equator completes a rotation in about 25 days, while the poles take closer to 35. This differential rotation stretches and twists the magnetic field lines threading through the convective zone. Over time, those field lines get wound tighter and tighter, amplified, concentrated. Eventually, they break through the surface. This is the solar dynamo. It's the engine that generates the sun's magnetic field. It operates entirely within the convective zone, driven by that combination of convective churning and differential rotation. The magnetic field it produces is not uniform or stable. It builds and decays on roughly an 11-year cycle. As it shifts, it creates the active regions, the sunspot clusters, the concentrated patches of intense magnetic activity that eventually trigger solar flares and coronal mass ejections. Everything covered in previous sections. The corona heating up to 2 million degrees, the flares releasing energy across the electromagnetic spectrum in minutes, the billion-ton plasma clouds hurled toward Earth. All of it traces back to this, to the convective zone grinding away beneath the surface, twisting magnetic fields until they snap. The violence we experience from the sun at a distance of 93 million miles is a downstream effect of what's happening in regions of incomprehensible pressure and temperature that we can't directly see and can't come close to replicating. And that's the part that should make you stop for a second. We have mapped the sun's surface in extraordinary detail. We've sent probes into the corona, measured the solar wind, cataloged sunspots in active regions and CME launch sites. Our understanding of solar physics has advanced enormously in the past few decades, but the interior of the sun remains largely opaque to direct observation. No signal we generate can penetrate the sun to image its core. No spacecraft can approach closely enough to sample the convective zone. The interior is inferred, not observed. What we do have is helioseismology, the study of oscillations on the sun's surface. The sun rings like a bell, vibrating in millions of different modes simultaneously. The way those vibrations propagate tells us something about the structure and behavior of the interior beneath. It's an indirect method, a sophisticated one, but still fundamentally a technique of inference. We are reading the sun's vibrations and working backward to conclusions about a region we cannot touch. This is not a criticism. It's an extraordinary scientific achievement to learn as much as we have about the solar interior from surface measurements alone. But it does mean that our picture of what's happening inside the sun is a model, not a direct observation. Models are tested, refined, improved, and occasionally surprised. We are reading the star's heartbeat from the outside. Educated guesses about what's happening in regions we can never directly observe. Most of the time that works. Let's move away from the sun now and talk about something that comes from a different direction entirely. From within our own solar system, from the dark spaces between orbits. Everything we've covered so far has been about the sun, what it does to us from above, what's churning inside it below the surface. But the solar system doesn't end at the corona, and the threats don't all come from the same direction. Some of them are orbiting quietly in the dark right now, following paths that cross Earth's path, and we haven't found most of them. That's the part that's worth sitting with. Scientists estimate there are roughly 4,700 potentially hazardous asteroids larger than 100 meters in orbits that bring them close enough to Earth to matter. As of the most recent surveys, we've identified about 30% of them. 30%. The other 70% are out there, untracked, unnamed, following orbits we haven't mapped. We don't know where they are. We don't know when they're coming. We just know statistically that they exist. Before we get into what that actually means, it's worth understanding what potentially hazardous means in technical terms. It's not a vague category. An asteroid earns that label if it's larger than 460 feet, roughly 140 meters in diameter. And if its orbit brings it within 4.65 million miles of Earth. That sounds like a comfortable distance. It's not. In orbital mechanics, that's close enough that small gravitational interactions with Earth, with the Moon, with other planets, can nudge a trajectory in significant ways over time. Close approaches are not one-time events. They repeat. And each pass is a new calculation. Size matters enormously in this conversation. A 20-meter object is relatively small. A 140-meter object is a city killer. A kilometer-wide rock is a regional catastrophe that alters global climate. And at 10 to 15 kilometers, you're in Chicxulub territory, the scale of the impact that ended the Cretaceous, killed the non-avian dinosaurs, and reset the history of life on this planet. The difference between those outcomes is just a matter of how large the rock is, and we don't know the sizes of the ones we haven't found. The Chelyabinsk event in February 2013 is the most instructive case study we have. On the morning of February 15th, a rock about 20 meters across entered Earth's atmosphere over Russia at roughly 40,000 miles per hour. Nobody saw it coming. It wasn't on any watch list. It wasn't being tracked. It simply arrived. The object never reached the ground. It disintegrated in the upper atmosphere in what's called an airburst, releasing energy equivalent to roughly 30 Hiroshima bombs. The shockwave shattered windows across 6 cities. About 1,500 people were injured, nearly all of them from flying glass. Think about that. A 20-meter rock, smaller than many houses, that never even touched the ground put 1,500 people in emergency rooms. Now scale that up. A 140-meter object doesn't airburst. It reaches the surface. The impact energy is measured in hundreds of megatons. If that happens over open ocean, you're looking at tsunamis that could devastate coastlines hundreds of miles away. If it hits a city directly, the city is gone. The crater is miles wide. The fireball, the blast wave, the ejecta, nothing in the immediate region survives. And a 140-meter object is right at the lower end of what we officially classify as potentially hazardous. There are almost certainly thousands of them we haven't cataloged. Go up an order of magnitude to a 1-kilometer rock, and you're in different territory entirely. The impact energy approaches 1,000,000 megatons. The initial blast is catastrophic, but what follows is worse. Dust and debris lofted into the stratosphere, blocking sunlight, collapsing food chains. We're talking about a global agricultural crisis lasting years. A 1-kilometer impactor doesn't just destroy a city or a country. It threatens civilization as a functioning system. And we have found only a fraction of the near-Earth objects in that size range. Here's where things get uncomfortable in a specific way. The Chelyabinsk rock came from the direction of the sun. That's not a coincidence. Objects approaching from the sunward direction are extraordinarily difficult to detect because telescopes can't point at the sun. Our ground-based survey programs are systematically blind to an entire region of the sky. Any asteroid on a sun-approaching trajectory essentially has a permanent advantage over our detection systems. We're watching the dark half of the sky quite well. The bright half, the dangerous half, we largely can't see. This detection gap has driven international efforts to build better observation infrastructure. Ground-based radar systems can pick up objects at shorter ranges, and space-based telescopes like the one on the Near-Earth Object Surveyor mission scheduled for launch in the coming years are designed specifically to see the sunward side of Earth's orbit that ground telescopes cannot. The point is not that the problem is unsolvable. It's that it requires resources, coordination, and sustained attention. It also requires that we fund these programs continuously, not in bursts. A gap in funding, a gap in observation, and suddenly you have months or years of the dangerous sky going unwatched. Apophis is the asteroid that planetary defense experts talk about most. It's a roughly 370-meter rock, well within city-killer range. And in April 2029, it will pass closer to Earth than the satellites in geostationary orbit. That's about 19,000 miles. For perspective, the Moon is about 239,000 miles away. Apophis will be 10 times closer than the Moon, close enough that people in the right part of the world will be able to see it with the naked eye, moving visibly across the sky. The 2029 flyby itself is not a threat. We're confident about that. But here's the thing about close passes. When Apophis passes through Earth's gravitational field that closely, Earth's gravity will alter its orbit. The question is how. The answer depends on exactly which part of Earth's gravitational field the asteroid passes through. Scientists have identified what they call a keyhole, a specific narrow region of space, only a few miles wide, within Apophis's trajectory. If the asteroid passes through that keyhole in 2029, Earth's gravity will reshape its orbit in a way that makes a future impact possible, specifically in 2036. If it misses the keyhole, which current projections suggest it will, no impact. The margin we're talking about is miles, measured across an asteroid's path across a gravitational field 240,000 miles closer to us than the Moon. That is not a comfortable margin. Understanding the keyhole requires understanding something deeper about orbital mechanics. When an asteroid passes through a gravitational field, its path curves like a ball rolling over a sphere, slightly but measurably. If that curve happens at just the right point in the asteroid's trajectory and at just the right angle and with just the right velocity, then the subsequent orbit can align with Earth's orbit again on the next pass. That's the keyhole. The calculation requires knowing the asteroid's mass, its velocity, its exact trajectory, and the density distribution of Earth's gravitational field. Uncertainties in any of these parameters compound into uncertainties in the keyhole's location, and the keyhole is already small. Add measurement uncertainty to small spaces, and you're trying to predict whether a specific dart will hit a dartboard that might be slightly to the left or right of where you think it is. The broader issue is that Apophis is a known object. We've been tracking it since 2004. We have 20+ years of observations. We've run the orbital calculations thousands of times, and we're still watching the 2029 pass carefully, because even with all that data, the keyhole question has only recently been resolved with confidence. Now imagine the same scenario with an object we discovered last month, or last week, or haven't discovered yet. In 2024, an asteroid designated 2024 YR4 was discovered on a trajectory that initially showed a non-trivial chance of hitting Earth. It was a genuine scare. Within weeks, additional observations refined the orbital calculation and moved the impact probability down sharply, in this case, toward the Moon rather than Earth. But that sequence of events, discovery, alarm, recalculation, revised assessment, played out in real time for a rock that had only just been found. The discovery pipeline is not designed for certainty. It's designed for iterative refinement. Astronomers find the object, analyze the data they have, compute probabilities, and then watch closely as more telescopes train on the target and add more data points. With each new observation, the orbital picture sharpens. But in that early window, before the picture sharpens, before hundreds of observations have been added to the database, there can be genuine uncertainty about whether an asteroid poses a threat. That is not a comfortable process to watch from the outside, and it's going to happen again. Planetary defense is a real field now, not a theoretical one. In September 2022, NASA's DART spacecraft deliberately collided with Dimorphos, a small moon orbiting the asteroid Didymos, and changed its orbital period by 32 minutes. That's more than 10 times what mission planners had set as their minimum success threshold. It worked. We proved that kinetic impactor technology is viable, that a spacecraft can hit a moving target in space and meaningfully alter its path. That's a genuine breakthrough. But DART hit a known target. Scientists had been studying Didymos for years. The spacecraft launched in November 2021 with a target that was already well characterized. The mission had a full development cycle, extensive ground truth data, and the luxury of time to prepare. The impact happened on September 26, 2022, almost a year after launch. And Dimorphos posed no actual threat to Earth. It was a test case. DART was a genuine triumph, but it required years of preparation, a well-characterized target, and a lot of lead time. 3 things you do not have when the asteroid is unknown. Asteroids are the known unknowns of planetary defense. We know they're out there. We're working on finding them. We have at least a theoretical framework for dealing with them. Comets are something else entirely. They come from the outer reaches of the solar system. They travel in orbits so elongated that they spend most of their existence far beyond the planets. The ones that pose the greatest danger are often ones we've never seen before. The distinction matters more than most people realize. When we talk about the asteroid threat, we're talking about a cataloging problem, a finite population of objects that, in principle, we can find and track. The comet threat is different in a way that makes it fundamentally harder to solve. Let's start with the basic divide. Comets come in 2 broad categories, and the difference between them is where they originate. Short-period comets, meaning those with orbital periods of roughly 200 years or less, come from the Kuiper Belt, the region of icy debris that extends from roughly Neptune's orbit outward to about 1,000 astronomical units from the Sun. These comets are manageable, relatively speaking. We've seen most of them come and go. Halley's Comet is the most famous example, returning to the inner solar system roughly every 75 years. We know its orbit. We can predict its return centuries in advance. Short-period comets are tracked, studied, and accounted for in the same systematic way we track near-Earth asteroids. They're not a comfortable thing to have in the neighborhood, but they're a known quantity. Long-period comets are a different category of problem. These objects originate from the Oort cloud, a vast shell of icy debris that extends tens of thousands of astronomical units from the Sun. Their orbital periods can be hundreds, thousands, or even millions of years. Many of them have never passed through the inner solar system before. They spend the overwhelming majority of their existence in conditions so cold and so distant that they're essentially frozen in place, invisible against the blackness of deep space. When a gravitational disturbance sends one falling inward, it begins a journey that might take thousands of years to bring it anywhere near Earth. The final approach, though, the phase where it's actually detectable, where it's bright enough and close enough to show up in our surveys, might give us only months of warning. Months. For an object that could be several kilometers across, traveling at speeds far higher than any asteroid we typically track. Here's where the velocity problem matters. A comet falling into the inner solar system from the Oort cloud can be traveling at 30, 40, even 60 kilometers per second when it crosses Earth's orbit. An asteroid in a near-Earth orbit is typically moving somewhere between 15 and 20 kilometers per second. That difference in velocity means a comet of the same mass carries significantly more kinetic energy than an asteroid. Kinetic energy scales with the square of velocity. If you double the speed, you quadruple the energy. A long-period comet impact isn't just bad in the same way an asteroid impact is bad. It's worse. For the same size object, by a factor that can reach several times the asteroid impact energy. And because the warning time is so short, the deflection methods we've been developing, kinetic impactors, gravity tractors, all of it, require years of lead time to be effective. With months of warning, there is no good option. The most vivid demonstration of what cometary bombardment actually looks like didn't happen here. It happened at Jupiter in the summer of 1994. If you weren't watching astronomy news at the time, it's worth knowing what the world witnessed. Comet Shoemaker-Levy 9 had been captured by Jupiter's gravity and torn apart by tidal forces into a chain of at least 21 distinct fragments. Over the course of 6 days in July 1994, those fragments fell into Jupiter one after another, each impact releasing energy measured in the hundreds of gigatons. The scars left behind in Jupiter's atmosphere were enormous, dark churning marks larger than Earth's entire diameter. Some of them were visible through amateur telescopes from the ground. The largest impact left a bruise in Jupiter's clouds that persisted for months. Astronomers watching through the Hubble Space Telescope described it as seeing the planetary equivalent of a shotgun blast, spread across the face of the largest planet in the solar system. That happened within our solar system in living memory, not millions of years ago, 1994. Jupiter plays a role in this that's worth understanding. Because of its enormous mass, Jupiter acts as a gravitational vacuum cleaner of sorts. Its gravity captures or deflects a significant number of objects that might otherwise continue inward toward the terrestrial planets. Shoemaker-Levy 9 itself is an example of Jupiter capturing a comet rather than letting it pass. Some models suggest that without Jupiter's influence, the inner solar system would experience far more frequent large impacts than it does. Jupiter isn't doing this intentionally, obviously. It's just a consequence of having a planet with over 300 times Earth's mass sitting in the outer solar system. But Jupiter isn't a perfect shield. Comets reach the inner solar system regularly. Some of the most spectacular comets in recorded history, Hale-Bopp, Hyakutake, McNaught, came from the outer solar system and passed through without incident. They were the lucky ones, in the sense that their trajectories didn't bring them anywhere near Earth. The ones we see are the ones that announce themselves. The ones that concern planetary scientists are the ones that don't give us that kind of advance notice. There's also the composition question, which doesn't get discussed enough. Comets aren't just dirty snowballs in the way that phrase sometimes gets used. They're complex mixtures of water ice, carbon dioxide, carbon monoxide, methane, ammonia, and a variety of organic compounds. When a comet enters the inner solar system and begins to warm, those volatile materials sublimate, producing the coma and the tails we associate with cometary appearance. A comet impact on Earth wouldn't just be an energy delivery event. It would also inject an enormous quantity of volatile gases and organic material into the atmosphere. The environmental effects of a major comet impact would differ in important ways from a rocky asteroid of similar size. Those differences aren't necessarily in our favor. Think about the 1994 Jupiter impacts again. Each of those fragments was relatively small compared to the full original comet. The energy released was still extraordinary. Now imagine that comet on a trajectory toward Earth instead. Jupiter wasn't always there to intercept it. The orbital architecture of the early solar system was different, more chaotic, with the giant planets migrating into their current positions over millions of years. During that period of rearrangement, the rate of large impacts on Earth and the other terrestrial planets was dramatically higher, which brings us to the uncomfortable dual nature of comets, because they're not simply a source of catastrophe. Early in Earth's history, during the period sometimes called the Late Heavy Bombardment, roughly 4 billion years ago, cometary impacts are thought to have been one of the primary delivery mechanisms for water and organic molecules. The oceans covering most of Earth's surface may owe some of their origin to cometary ice. The organic chemistry that eventually became biology may have arrived in part from the outer solar system. Comets aren't invaders that evolved separately from Earth's story. They're part of it, woven into the origin of the very thing we're trying to protect. That doesn't make the threat less real. It makes it stranger. The same objects that may have seeded Earth with the building blocks of life are capable of erasing everything that built itself from those blocks. The Oort cloud is perhaps the most unsettling structure in the solar system, precisely because we can't see it. Every other threat we've talked about in this video has a physical presence we can point to. Solar flares light up our instruments. Asteroids show up as moving dots in telescope surveys. Comets grow bright tails as they fall toward the sun. The Oort cloud gives us none of that. It has never been directly observed. No telescope has imaged it. No spacecraft has reached it. It exists, as far as our instruments are concerned, entirely as an inference, a theoretical shell of icy debris that astronomers believe must be out there because of the comets that keep arriving from it. We know it's real the same way you'd know a beehive is somewhere nearby if bees keep showing up. You haven't seen the hive. But the bees are real, and they had to come from somewhere. So let's talk about the scale of this thing, because the numbers are genuinely difficult to process. The inner edge of the Oort cloud is estimated to begin somewhere between 2,000 and 5,000 astronomical units from the Sun. 1 AU is the distance from Earth to the Sun, about 93 million miles. The outer edge is thought to extend to roughly 100,000 AU. That puts the outer boundary somewhere between a quarter and halfway to the nearest star. This isn't a ring. It isn't a flat disk like the Kuiper Belt. The Oort cloud is a roughly spherical shell surrounding the entire solar system in every direction, like an enormous hollow globe with our sun sitting at its center. Here's a number that helps frame the distance. Voyager 1 is the farthest human-made object ever launched into space. It was sent out in 1977. It has been traveling away from Earth for nearly 50 years, and right now it's about 160 AU from the Sun. That feels like a lot. It isn't. At its current speed, Voyager 1 will take approximately 300 years just to reach the inner boundary of the Oort cloud, and then it will take another 30,000 years to pass through it entirely. 30,000 years. That's longer than recorded human civilization by a factor of 6. It's not a misprint, and it's not an exaggeration. The solar system is simply that large in its outer reaches, and our fastest spacecraft barely scratches the edge of it on any timescale that means anything to a human being. Now let's talk about what's actually out there. The Oort cloud is thought to contain somewhere between 1 trillion and several trillion individual objects, icy bodies ranging from small chunks to objects hundreds of kilometers across. These aren't packed together the way you might picture them. The distances between individual objects are so enormous that even with 1 trillion of them out there, The cloud is mostly empty space. If you were somehow transported into the middle of the Oort cloud, you almost certainly wouldn't be able to see another object with the naked eye. Each one is alone in the dark, separated from its nearest neighbor by millions of miles, slowly tracing an orbit so wide that a single trip around the sun takes millions of years. Think about that for a second. These objects have been orbiting the sun since the solar system formed, roughly 4.5 billion years ago. In all that time, many of them may not have completed a single full orbit. They are so far out, moving so slowly, that they're essentially just sitting there, preserved at near absolute zero, locked in deep freeze, untouched since the early solar system scattered them into the outer dark. That's where the real problem starts. They're not locked there permanently. The Oort cloud objects sit at the very edge of the sun's gravitational influence, which means it doesn't take much to disturb them. The sun holds on to them, but barely. And the universe around them is not quiet. Passing stars exert gravitational tugs as they move through the galactic neighborhood. Giant molecular clouds, enormous concentrations of gas and dust drifting through the galaxy, can shift the trajectories of Oort cloud objects as the solar system passes through or near them. Then there's the galactic tide itself, the slow gravitational pull of all the mass in the Milky Way acting on the outer solar system, constantly warping and flexing the orbits of objects at the cloud's outer edge over millions of years. The cumulative effect of these forces is to maintain a state of perpetual disturbance in the outer cloud, constantly redistributing objects and altering their orbital paths in subtle but significant ways. Any one of these forces can nudge an object out of its stable orbit. When that happens, the object doesn't stay put. It starts to fall. That fall is slow at first. An Oort cloud comet dislodged from the outer edge might take thousands to tens of thousands of years to make its way into the inner solar system. It's in free fall, falling inward from 50,000 AU, picking up speed as it goes. For most of that journey, it's cold and dark and entirely invisible. There's no tail. There's no reflected sunlight bright enough to detect from Earth. There's nothing. We would have no idea it was coming. The discovery of long-period comets throughout recent astronomical history underscores this vulnerability. Between 2020 and 2023, several comets previously unknown to observers appeared with little advance warning, their trajectories visible only when they had already entered deep into the inner solar system. Modern detection systems have improved our ability to spot these objects, but remain fundamentally limited by the laws of physics. A comet is only detectable once it's relatively close to the sun. In cosmic terms, relatively close still means months or years of travel time ahead. This compression of warning time is precisely what makes long-period comets such enduring threats to Earth. Only when a long-period comet gets close enough to the sun does the ice begin to sublimate, releasing gas and dust that form the characteristic bright coma and tail we associate with comets. By that point, it's already deep in the inner solar system. The warning window is short, sometimes months, sometimes a year or two. For a comet coming in from the Oort cloud for the very first time on a trajectory that puts it on a collision course with Earth, there may not be enough time to do anything about it. As we covered with comets, deflection at that stage is essentially off the table. That's the nature of the threat the Oort cloud represents. It's not one specific object we can track and monitor. It's a reservoir of 1 trillion potential impactors, held in delicate gravitational balance by a sun whose influence at that distance is being constantly countered by forces from outside the solar system entirely. The Oort cloud is less a structure and more a condition, a standing inventory of cosmic hazard that we cannot survey, cannot catalog, and cannot watch. What we do know is that the cloud isn't static. It has never been static. Every time the solar system passes near another star, every time a molecular cloud drifts across our path, every time the galactic tide flexes the outer orbits by a fraction of a degree, some number of objects are pushed onto new trajectories. Some of those trajectories lead inward. Most of those inbound objects will miss every planet in the solar system entirely and either swing around the sun and head back out, or get captured into shorter orbits, or eventually leave the solar system altogether. The odds that any specific one of them hits Earth are very small, but small odds applied to 1 trillion objects, repeated over millions of years, produce events. They always have. The geological and fossil record shows that large impacts have happened throughout Earth's history. The late heavy bombardment, roughly 4 billion years ago, suggests a period of intense cometary and asteroidal bombardment that may have been triggered by gravitational upheaval in the early solar system. Studying what caused it and whether similar large-scale perturbations could happen again requires understanding the Oort cloud and the forces that shape it. We're still working on that. Before we get too comfortable with the idea that this is all ancient history, it's worth sitting with the basic fact that the mechanisms responsible for past bombardment events are still operating right now. The galactic tide is still pulling on the outer solar system. Stars are still passing through the solar neighborhood. The Oort cloud is still responding to those forces. Objects that were nudged off stable orbits 1 million years ago are still in the middle of their long fall inward. We can't see them yet. We won't for a long time. Some of those trillion objects may already be falling inward, set in motion by a stellar encounter that happened 1 million years ago, and we won't know until they get close enough to reflect sunlight. The sun is not sitting still, and neither is anything around it, and that fact alone should change how you think about the solar system. We tend to picture the solar system as something fixed, a diagram on a classroom wall, the sun at the center, planets in their lanes, everything orbiting neatly in place. That picture is useful, but it leaves out something important. The sun is moving. It orbits the center of the Milky Way at roughly 500,000 miles per hour, dragging everything with it, every planet, every asteroid, every one of those trillion objects in the Oort cloud. The entire solar system is traveling through the galaxy, and the galaxy is not empty. Other stars are out there, moving along their own paths, on their own schedules, and occasionally those paths bring them close to ours. Here's where things get uncomfortable. When astronomers talk about a close stellar encounter, they mean something very different from what that word suggests. A star passing within a light year or two of the sun would never be visible to the naked eye as anything unusual. You would have no idea it was there without a telescope and careful measurement. But at that distance, its gravitational influence reaches deep into the outer Oort cloud. The objects sitting out there at 50,000 or 100,000 astronomical units, barely bound to the sun at all, feel the pull. Orbits shift. Trajectories that were stable for millions of years suddenly aren't. some of those objects get nudged inward. They begin the long fall toward the sun and eventually toward the inner solar system, toward us. These events don't happen on human timescales. We're talking about encounters that occur every few million years, disturbances that take thousands of years to translate into comets arriving near Earth. But they have happened repeatedly. Throughout Earth's entire history, the solar system has been passing through the galaxy, brushing near other stars and getting its outer edges rearranged. The fossil record carries traces of what that looks like. Mass extinctions, some scientists have argued, show a rough periodicity, spikes in extinction rates separated by tens of millions of years. Something, the argument goes, keeps triggering comet showers. That argument led to the Nemesis hypothesis. For decades, some researchers proposed a specific mechanism. The Sun, they suggested, has an unseen companion star, a small, dim object, a red dwarf or brown dwarf, on a highly elliptical orbit that carries it into the outer Oort cloud every 26 to 30 million years or so. Each passage would gravitationally disturb millions of objects, sending a wave of comets toward the inner solar system and increasing the probability of Earth impacts. The periodic mass extinctions, including the one that ended the dinosaurs, might be fingerprints of this invisible companion. They called it Nemesis. The hypothesis generated serious scientific attention. It also generated extensive sky surveys looking for any candidate companion star. None was found. The Nemesis hypothesis has largely been set aside at this point. But that doesn't mean the underlying mechanism is wrong. Stellar perturbations of the Oort cloud are real. They happen regardless of whether there's a specific companion. Passing stars don't need to be in a fixed orbit to disrupt what's out there. Any star passing close enough will do the job. Nemesis may not exist, but the process Nemesis was invented to explain is still operating. Which brings us to something discovered in 2015 that most people have never heard of. Schultz's star is a red dwarf, a dim, small, cool star, currently sitting about 20 light-years from the Sun. Unremarkable at first glance, but astronomers studying its motion traced its trajectory backward and found something striking. About 70,000 years ago, Schultz's star passed within approximately 0.8 light-years of the Sun. Think about that distance relative to what we've been discussing. The outer Oort cloud extends to roughly 1 light-year from the Sun. Schultz's star didn't just come close, it passed through the outer Oort cloud itself, 70,000 years ago. Anatomically, modern humans were already walking the Earth. Some of our ancestors may have looked up at that star on a clear night and seen it as a slightly brighter point of light than usual, with no way of knowing what its gravity was doing to the frozen objects at the edge of the solar system. We didn't discover this until 2015. We worked it out retroactively, calculating backward from the star's current position and velocity. That's a sobering thing to sit with. A star penetrated our solar system's outer boundary within human prehistory, and we only figured that out half a century into the space age. Whatever it dislodged from the Oort cloud during that passage is now somewhere on an inbound trajectory, potentially tens of thousands of years into a fall that will eventually bring it to the inner solar system. Or it was redirected outward. We don't know. We can't know. We can only note that it happened. Now pull back even further. Individual stars passing by are one mechanism, but there's a larger force at work, one that operates constantly rather than periodically. the galactic tide. Every object in the Milky Way exerts gravitational influence on every other object. The combined pull of hundreds of billions of stars, plus the dark matter distributed throughout the galaxy, plus the gas and dust in the galactic disk, all of that mass produces a tidal force on the outer solar system. It's not dramatic. It doesn't announce itself. But over millions of years, it steadily warps the orbits of Oort cloud objects, gradually raising and lowering the points where those orbits approach the Sun. It's the same basic mechanism as tidal forces between the Earth and Moon, just operating on galactic scales over astronomical timescales. This is not a theoretical concern for the distant future. It's happening right now. The galactic tide has been acting on the Oort cloud for the entire history of the solar system. Researchers who model long-period comet delivery, trying to explain why comets arrive from the inner Oort cloud at the rate they do, find that galactic tidal forces account for a significant fraction of them. The galaxy itself is sending objects toward us, slowly and continuously, through the gravitational influence of its own structure. The solar system, from that perspective, is not a sealed container. It's more like a house with walls made of mesh. Things pass through. The outer reaches of our own system are being continuously stirred by forces that have nothing to do with the Sun or any of its planets. A stellar encounter hundreds of light years away. A dense molecular cloud the Sun passed through millions of years ago. These leave traces in comet populations and orbital distributions that we can detect if we look carefully enough. Before we get too philosophical about this, it's worth being precise about what it means in practical terms. The probability of a Oort cloud perturbation producing an Earth-threatening comet on any given human lifetime is extremely small. Billions of objects in the outer Oort cloud, and the vast majority stay where they are. Perturbations dislodge a small fraction. Most of those fall inward over thousands of years, pass through the inner solar system, and swing back out without incident. The Earth is a small target, but the sheer number of objects involved means the process produces results. Long-period comets do arrive. Some have come alarmingly close. And unlike near-Earth asteroids, which we're gradually cataloging, long-period comets from the outer Oort cloud arrive with very little warning. There is no survey that would show us a comet 10,000 years before impact. We would see it only in the final stages of its journey. By then, the galactic tide would have done its work millions of years ago. The Sun has orbited the Milky Way roughly 20 times in its 4.6 billion-year history. Each orbit takes about 225 million years. Each orbit brings the solar system through different regions of the galaxy, closer to dense star clusters in some eras, through spiral arms rich with molecular clouds in others. Each of those environments exerts its own perturbative influence on the Oort cloud. The solar system we live in today carries the accumulated gravitational history of 20 full laps around the Milky Way. Everything out there in the Oort cloud has been nudged, jostled, and redistributed by every star the Sun has passed near, every massive cloud it has moved through, and the slow, constant pull of the galactic disk bearing down from above and below. We are not in a quiet corner of the universe. We are embedded in it, subject to its forces, connected to its structure in ways that reach all the way down to the long-period comets that occasionally light up our skies. The threats we can see, the asteroids and the cataloged comets, are only the ones that have already made it to the inner solar system. The reservoir that feeds that threat is orders of magnitude larger, sitting at the edge of everything we've ever sent a spacecraft near, being shaped by the galaxy even now. Our solar system is not a closed system. It's a porous, permeable neighborhood being slowly rearranged by gravitational forces that originate light years away. Somewhere in the space between stars, right now, there are planets, entire worlds, possibly as large as Jupiter, traveling in total darkness with no star to orbit, no sunrises, no warmth, no light of any kind, just frozen rock and ice drifting through the void at tens of thousands of miles per hour, completely invisible against the black backdrop of interstellar space. We call them rogue planets, and the Milky Way may contain billions of them. Some estimates push that number into the trillions. We don't actually know, because we can barely detect them at all. That invisibility is part of what makes them unsettling. A star announces itself across enormous distances. You can see it, track it, measure its motion, predict where it will be in 10,000 years. A rogue planet gives you almost nothing to work with. It emits no light of its own. It reflects no starlight because there's no star nearby to reflect. The only way to detect most of them is through gravitational microlensing, a technique where the planet's gravity briefly bends and brightens the light of a more distant star behind it, producing a telltale spike in brightness that lasts a few hours or days. You can confirm a rogue planet passed by. You can't tell where it's going next. So how do they get out there in the first place? The answer goes back to the violence of planetary formation. When a star system is young, the planets don't simply settle into their current orbits peacefully. They migrate. They interact gravitationally with the disk of gas and dust they formed from, and they interact with each other. In the early chaos of a forming solar system, close gravitational encounters between planets are common, and those encounters can fling a planet completely out of the system entirely. Jupiter-mass planets are especially good at this. Their enormous gravity acts like a slingshot, and smaller planets near them during the system's formative period are often thrown outward with enough velocity to escape the star's gravity entirely. Our own solar system almost certainly did this. There are models of the early solar system, particularly variations of what's called the NICE model, that suggest our gas giants went through a period of dramatic orbital reshuffling roughly 4 billion years ago. During that reshuffling, there may have been a fifth giant planet, something comparable in mass to Uranus or Neptune, that was gravitationally scattered by Jupiter and ejected into interstellar space. The solar system we live in today may be the survivor of a more crowded early arrangement that didn't make it through intact. That lost world, if it existed, is somewhere out there right now. Drifting. Cold. Utterly unreachable. The mechanisms by which this happens are well established in planetary dynamics. When a massive object enters a system, gravitational interactions follow predictable mathematical laws, governed by the orbital mechanics principles that control everything from satellite launches to the motion of galaxies. Numerical simulations of such encounters show that even a small change in the mass of the intruding object, or a slight variation in its trajectory, can produce vastly different outcomes. Some simulations result in the ejection of planets from the system. Others show the intruding object being captured into a long eccentric orbit. Still others demonstrate the formation of entirely new orbital configurations. The violence of these interactions can persist for millions of years, with the system gradually settling into new equilibrium only after the massive disruption has run its course. Here's where things get uncomfortable again. Most discussions of rogue planets treat them as a distant curiosity, something interesting to study through microlensing surveys, but not a practical concern. That framing is probably correct on human timescales, but the galaxy is 13 billion years old, and the solar system has been moving through it for 4.5 billion of those years. The odds of a rogue planet passing close enough to affect our solar system in any given century are extraordinarily small. That much is true. But extraordinarily small and impossible are not the same thing. And what would a close encounter actually look like? It depends heavily on how close is close. At very large distances, thousands of AU or more, a passing rogue planet might perturb the outer Oort cloud in ways we'd never notice directly. Some objects get nudged onto slightly different orbits. A few of them, over thousands of years, fall inward and become long-period comets. The encounter itself would be invisible. We'd only see the downstream effects much later, and we might not even connect them to a cause. Closer encounters are a different matter. An Earth-mass rogue planet passing within, say, a few hundred AU of the Sun could scatter Kuiper Belt objects significantly, pushing some of them onto crossing orbits with the inner solar system. The outer planets themselves could experience measurable orbital perturbations over long timescales. Nothing catastrophic on human timescales, perhaps, but meaningful disruption to a solar system architecture that has been stable for billions of years. A Jupiter-mass rogue planet passing that close would be far more disruptive. Jupiter is not just a planet. It's a gravitational anchor for the entire outer solar system. Introduce another object of comparable mass on a hyperbolic trajectory through the outer solar system, and the effects on the gas giants, the Kuiper Belt, and the Oort cloud would be significant and potentially long-lasting. The probability of this happening is low. The consequences if it did would not be low at all. One of the stranger aspects of this threat is that we might get very little warning. Scholz's star, the red dwarf that passed within 0.8 light-years of the Sun about 70,000 years ago, was only identified in 2015. We figured out it had already happened by working backward from its current velocity and trajectory. A rogue planet is harder to detect than a star by orders of magnitude. Current survey telescopes can find some of them through microlensing, but a rogue planet approaching the solar system from the right angle, at the right speed, might not be detected until it was already well inside the Oort cloud. At that point, depending on its trajectory, we'd have centuries of warning, or we'd have decades, and there's a meaningful difference between those two outcomes. Astronomers using data from surveys like the Optical Gravitational Lensing Experiment, and more recently, the Roman Space Telescope program, have been refining estimates of the rogue planet population. The current best estimates suggest they may outnumber stars in the galaxy. Think about that for a second. More planets than stars, all of them untethered, all of them dark, scattered through the spaces between solar systems in numbers that strain comprehension. Most of them will never come close to anything. They'll drift through the void for longer than the current age of the universe, passing through empty space at distances so great that their gravity never meaningfully interacts with any other body. But some of them won't. The galaxy is large, but it's not infinite, and probability doesn't disappear just because the numbers are small. There's something else worth sitting with here. These worlds formed around stars. At least some of them spent time in young solar systems. absorbing heat, possibly accumulating atmospheres, possibly even developing conditions on their surfaces that were interesting in ways we don't fully understand. Then they were thrown out. Their star's light receded behind them over thousands of years as they accelerated away. Whatever warmth existed on their surfaces cooled and froze. Whatever atmosphere they had may have collapsed and frozen to the ground. They've been in the dark ever since. Some of them have been out there for 10 billion years, frozen solid at temperatures near absolute zero, carrying the chemical record of a solar system that may not even exist anymore, orbiting nothing, going nowhere in particular. They've been out there, in the cold and the dark, for longer than Earth has existed, and we wouldn't see most of them coming until they were already close. Now let's pull back and look at all of this together, because each of these threats doesn't exist in isolation. They're all part of the same layered system we live inside. That's the part that tends to get lost when you look at any one of these topics on its own. You read about solar flares, and it sounds like a solar problem. You read about the Oort cloud, and it sounds like a distant, abstract problem. But they're not separate categories of danger sitting on different shelves. They're connected. They feed into each other. And the same processes that make life on Earth possible are, in many cases, the exact same processes that make it fragile. Start at the center. The sun's core is running fusion reactions at 15 million Kelvin, producing energy that takes roughly 20 million years to work its way to the surface. That energy doesn't just heat the photosphere, it drives the convective zone, where plasma rises and falls in churning columns the size of states. That convection, combined with the sun's differential rotation, is what generates the magnetic dynamo. And the magnetic dynamo is what produces sunspots, solar flares, coronal mass ejections, and the 2 million degree corona sitting above all of it. None of those surface phenomena are random. They trace directly back to what's happening deep inside a sphere of plasma we can't directly observe. The violence that threatens our satellites and power grids originates millions of kilometers below the surface and millions of years before it reaches us. Now add the solar wind. The corona is so hot that the sun's gravity can't hold it. So particles stream outward in every direction at roughly 1 million miles per hour. That flow extends past Earth, past Mars, past Jupiter, all the way out to somewhere between 100 and 150 AU from the Sun, where it finally runs into the interstellar medium and forms the heliosphere. Here's the thing about the heliosphere that most people don't appreciate. It's a shield. The solar wind pushes back against galactic cosmic rays, the high-energy particles streaming in from supernova remnants and other violent events across the galaxy. Without the heliosphere, the radiation environment at Earth's surface would be significantly worse. The sun, in other words, protects us from the galaxy even while it periodically threatens us with its own activity. That's not a minor detail. It means we are caught between two sources of radiation, and the thing that reduces one is, at times, the source of the other. When a major CME launches from the sun, it can travel at anywhere from 300 to 3,000 kilometers per second. The fastest events reach Earth in as little as 17 minutes after detection. At that point, power grid operators have 17 minutes to respond to something that, in a worst-case scenario, could knock out high-voltage transformers that take months to replace and aren't manufactured domestically. The Carrington event of 1859 induced currents strong enough to shock telegraph operators and run telegraph systems without external power. That was before the electrical grid existed, before pipelines with computerized pressure controls, before GPS-dependent navigation systems and satellite-based communications infrastructure. A Carrington equivalent event today doesn't just inconvenience people, it initiates cascades. Refrigeration for medications fails, fuel pumps stop, water treatment plants go offline, and the grid components most vulnerable to geomagnetically induced currents are the largest, most expensive, and most difficult to replace. We're not talking about a temporary blackout. We're talking about months. Then there's the asteroid layer sitting closer than most people realize. Roughly 4,700 potentially hazardous asteroids, larger than 100 meters, are estimated to be in orbits that bring them near Earth. We've found about 30% of them. The other 70% are real, are out there right now, and are on orbits we haven't mapped. Apophis is one we have found, 370 meters wide, passing closer to Earth than many operational satellites in 2029. That flyby isn't the danger, but it will pass through a gravitational keyhole, and that pass will determine whether future encounters become something more serious. Think about what 70% unknown actually means. For every known object we're tracking, there are roughly 2 more that we aren't. And that's just the asteroids large enough to cause regional devastation. The smaller ones, the Chelyabinsk-sized objects, 20 meters or so, number in the millions, and cataloging them all is essentially impossible. Go farther out, past Neptune, and you reach the Kuiper Belt and eventually the Oort cloud. The Oort cloud alone may contain 1 trillion icy objects, each on an orbit so loosely bound to the Sun that a passing star can dislodge it. Schultz's star passed within 0.8 light-years of the Sun, roughly 70,000 years ago. We only figured that out in 2015 by working backward from its current motion. It penetrated the outer Oort cloud. We don't know what it disturbed. Objects set in motion by that encounter could still be falling inward, on journeys that will take thousands of years to complete. We won't see them until they get close enough to reflect sunlight, at which point the window for any meaningful response compresses dramatically. This is the nature of the layered threat. Some of it arrives in 8 minutes at the speed of light. Some of it arrives after a 1,000-year journey from the outer solar system. Some of it, like the galactic tide slowly warping Oort cloud orbits, operates on timescales of millions of years. The timescales are completely different, but the system is the same system. Earth has already been on the receiving end of it. 4 billion years ago, during the late heavy bombardment, the inner solar system was subjected to a sustained period of intense impact activity as the giant planets migrated and destabilized the asteroid and Kuiper Belt populations. The Moon's cratered surface is the record of that era. 66 million years ago, a 10 to 15 kilometer impactor hit what is now the Yucatan Peninsula and ended the Cretaceous. The impact itself was catastrophic. The months-long impact winter that followed finished the job for most large animals on the planet. In 774 CE, tree rings from around the world recorded a sudden spike in carbon-14, so extreme that it required either a massive solar energetic particle event or a nearby gamma-ray burst to explain it. That event, whatever it was, deposited more radiation in Earth's atmosphere than anything else in the past 10,000 years. None of these are hypotheticals. They are documented history, The system has done this before, and here's where it gets uncomfortable in a specific way. The things that make Earth habitable are not separable from the things that make it vulnerable. The sun's magnetic activity, which creates the corona and drives solar flares, also drives the solar wind that forms the heliosphere that shields us from cosmic rays. The planetary formation process that built Earth also built the Oort cloud and seeded it with the same materials that were later assembled into habitable worlds. Jupiter's gravity, which acts as a partial shield by capturing or deflecting incoming objects, also played a role in scattering smaller bodies inward during the solar system's early history. You can't remove the threats without also dismantling the mechanisms that made the planet livable. Between the stars, by comparison, it's quiet. There's nothing out there. No charged particle flows, no magnetic field eruptions, no reservoirs of icy bodies held in unstable orbits. Just cold, diffuse hydrogen, the occasional photon, and the slow background hum of galactic cosmic rays. The void is empty. The void between the stars is quiet, cold, and mostly empty. And compared to what's happening in the sun's corona or lurking in the outer solar system, quiet and empty sounds almost peaceful. The good news, and there is some, is that we're not completely unprepared. There are people whose entire job is to watch the sun. NOAA's Space Weather Prediction Center operates around the clock, monitoring solar activity and issuing forecasts the same way meteorologists track hurricanes. The European Space Agency runs its own monitoring programs. NASA's Parker Solar Probe is currently flying closer to the sun than any spacecraft in history, collecting data on the corona, the solar wind, the magnetic structures that produce the events we've spent this entire video describing. The Solar Orbiter mission, a joint effort between NASA and ESA, is studying the sun's poles for the first time. Scientists' views they've never had before. These are serious programs staffed by serious scientists, and they've meaningfully improved our ability to see what's coming. Here's what we can actually do. When a coronal mass ejection launches from the sun, we can detect it almost immediately and estimate when it will arrive at Earth. That gives us somewhere between 1 and 3 days of warning for most events. That's enough time to put satellites into safe mode, warn power grid operators to reduce loads, alert airlines to reroute flights away from polar regions where communications fail first. Airlines, utility companies, and military operators all have protocols for space weather events now. That didn't exist 30 years ago. The improvement in forecasting capability over the past 2 decades has been real and significant. But here's where things get uncomfortable. All of that warning time is nearly useless for one critical variable. The magnetic field orientation of an incoming CME, whether the field is pointing north or south when it arrives, is what determines whether the event causes a catastrophic geomagnetic storm or passes mostly without consequence. A southward-pointing field reconnects with Earth's magnetosphere and drives energy into it. A northward-pointing field largely deflects, and we cannot reliably measure that orientation until the CME is about 15 to 60 minutes from Earth. By then, there's almost nothing left to do. The most important piece of information arrives when it's too late to act on it. That's not a gap we're close to closing. Planetary defense is in a better position than it was 10 years ago. The DART mission in 2022 was a genuine milestone. NASA deliberately crashed a spacecraft into an asteroid called Dimorphos and successfully changed its orbital period. It worked. The deflection was measurably larger than models predicted, partly because the impact ejected a significant amount of debris that added momentum to the push. ESA's Hera mission is now traveling to the Dimorphos system to study the crater and measure the full aftermath in detail. We learned something real, and we're going back to learn more. Congress has also mandated that NASA find 90% of potentially hazardous asteroids larger than 140 meters. That's the threshold where an impactor transitions from regional catastrophe to something with global consequences. The NEO Surveyor mission, an infrared space telescope designed specifically for this survey, will be a major step toward meeting that goal once it's operational. Infrared is important because asteroids that are dark and rocky absorb sunlight instead of reflecting it. Them nearly invisible to optical telescopes but detectable by their heat signature. NEO Surveyor is built to find the ones that are hardest to see. The problem is funding. The NEO Surveyor mission has faced repeated budget constraints that pushed its launch date back. Some estimates suggest completing the full 90% survey will take decades even after the telescope is operational. In the meantime, we're tracking roughly 30% of the hazardous objects in that size range. The other 70% are out there on orbits we haven't characterized. One of them could be on an approach trajectory right now and we wouldn't know it. And then there are the threats we genuinely cannot protect against. A long-period comet falling inward from the Oort cloud for the first time might be detected months before it reaches the inner solar system. At that point, deflection is effectively impossible. You'd need years of lead time to meaningfully change the orbit of an object that massive moving that fast. A few months gives you time to watch it arrive. There is no planetary defense protocol for that scenario because there's no planetary defense solution for it. A super flare is another category we're not equipped for. The Sun has produced flares orders of magnitude larger than anything in the modern instrumental record. We know this from proxy evidence, isotopes locked in tree rings, and ice cores that record spikes in cosmic radiation going back thousands of years. The 774 CE event, detectable in tree rings across the planet, would have been catastrophic for any civilization dependent on electrical infrastructure. We don't know what caused it with certainty. We don't know when something comparable will happen again. Our current forecasting systems are calibrated to events we've actually observed. An event significantly outside that range would overwhelm every warning system we have. Rogue planet perturbations of the Oort cloud are in a different category entirely, not something any monitoring program is designed to address. This was because the timescales involved are millions of years, and the effects are indirect. A rogue planet passing through the outer solar system wouldn't cause an immediate impact. It would nudge orbits, disturb the Oort cloud, potentially send objects inward on trajectories that take thousands of years to deliver them to the inner solar system. By the time those objects showed up in a telescope, the perturbation would be ancient history. Some of these scenarios have probabilities so low that they're effectively academic. A superflare large enough to sterilize the surface might happen once every few billion years, if at all. A rogue planet passing close enough to seriously disrupt the solar system is vanishingly unlikely on any human timescale. We're probably not going to experience those things. But a Carrington-level CME is not vanishingly unlikely. Estimates suggest something in that range happens roughly once per century. We are statistically overdue for one right now. A modern Carrington event would cause trillions of dollars in damage and potentially months of grid failure across large portions of the planet. That's not a hypothetical. That's a probability distribution we're living inside. The asymmetry of how we prepare for these things is hard to look at directly. The global defense budget runs into the trillions of dollars annually. Space weather research, planetary defense, and Oort cloud monitoring collectively receive a small fraction of that. The threats described across this entire video represent risks to every person on Earth, regardless of where they live or what politics they hold. A severe geomagnetic storm doesn't respect borders. A long-period comet doesn't have a nationality. The funding that supports our ability to see these things coming and do something about them is genuinely modest compared to what we spend defending against each other. We spend vastly more preparing for threats we can control than for the ones we can't. The universe has no particular interest in accommodating that choice.